This video is going to give some numerical examples of tracking with dual mode approaches. So the previous video gave the algebra for how advanced knowledge of the target could be integrated into an optimal predictive control setup, and it was shown that future values of the target have a direct and explicit impact on the perturbation term in the control law, so that the behavior deviates from the unconstrained optimal associated to a fixed target. And what we're going to do in this video is explore that impact in more detail by giving some numerical demonstrations. So what we know is the nominal predictions, if you have a fixed target and no constraints, basically follow these dynamics here. And we've still got this perturbation term here, which was designed primarily for constraint handling. So there we are, the perturbation term is used for constraint handling. However, what we showed in the previous video is it's also available to optimize performance in cases where the predictions are no longer optimal. And these predictions are no longer optimal when you have time-varying targets or a suboptimal terminal mode, and we're not going to worry about that detail, it was discussed earlier. So the key thing is these perturbation terms will be non-zero when you have time-varying targets, and that was shown in the previous video. So if we have a typical unbiased cos function, there it is there, then what we showed is that if you minimize that, then the perturbation term on the control law has a very particular dependence on the future targets. So we have a perturbation term to make use of advanced information on the target. So it says, you've given me some information, how do I need to change my control law to make use of this information? And this tells you explicitly what you do. There is also a term which tells you how the perturbations may vary if the terminal feedback is not optimal. But for this particular video, we're going to assume the terminal feedback is optimal, and so as we did in earlier chapters, you'll see that that SXC term is therefore 0. So what's the effect of advanced knowledge? By definition, if the set point is fixed, then the optimal state feedback is fixed. And we've done that earlier, and it comes from optimal control theory. Now what this tells you is that if the target is fixed, then the optimal perturbation term to the control law must be 0. That comes from optimal control theory. So in other words, if rk plus I equals rk plus 1 for all I greater than 1, then this C term must be 0, obviously in the unconstrained case. And what does that tell you? It tells you that this perturbation term that we've derived, that tells you how advanced information comes into the control law, must be 0 if this condition here holds. So if the target's fixed, then the perturbation term must be 0. So what I've done is I've said, okay, what does this tell me? Well, let's make the target fixed in the future, and you'll see that's what I've done here. I've said this R future term has got all the same values. And what that means is I can express that R future term as this matrix with lots of identities times the first one. And what I'm expecting is that this is 0. So if I go through the algebra, what that's telling me is that actually I have this identity here. The SC inverse times SCR times this matrix of identities must be 0. Now, why is that important? We can check this in MATLAB, and if your code does not give this, then you've got a mistake in your code. So let's look at this. We've got first example video 6.8 example 1, and what this file does is it creates the feed forward term PR, which is defined here as SC inverse times SCR. It also creates this matrix LL, and it will multiply the two together. And it will allow you to demonstrate that you've basically got a 0 steady state gain for all values of advanced knowledge if you assume that the target is fixed. Now the other thing you might notice, this is quite interesting, is the feed forward term has a very clear and transparent structure. And that's what you expect. If you look at optimal control theory, it will tell you that if you come up with a particular solution now and then you redo the optimization one sample later without changing any of the essentially the information, then you should get the same answer. And that structure is transparent when you look at the MATLAB solutions. So let's do that now. So there's my MATLAB window. is my file. So first of all, we've run this so far. Let's look at these terms. And so you'll see PR, and what do you notice? If NA equals 1, PR is essentially 0. Don't worry about the 10 to the minus 7, that's because of all the rounding errors that come with these large autonomous models. But essentially, you'll see that the PR is 0. So if NA equals 1, that's the same as saying I've got no advanced knowledge, and so this PR does nothing. What if NA equals 3? What do we get now? Well, if we look first of all at the PR term, you'll see this structure. You'll see a 0.4209 there, a 0.4209 there. So you can see there's this sort of structure developing. But the last column is slightly different because we need to satisfy this expression. PR times LL gives me 0. So if I look at PR times LL, what do you notice? You get 0. So we've checked it, and it says, yep, everything seems to be working fine. I can see a structure developing. NA equals 3 is quite small, and I've got this 0. What happens then if I take NA up to 5? What do we notice now? Well, here's my PR term, and you can see the structure, 0.4209, 0.4209, 0.4209, 0.4209. You look below, 0.3798, 0.3798. You can see it's got this striped structure, which is exactly what you expect from optimal control solutions. If I look at PR times LL, and what do you notice? You get 0. Now we do have another example. Here it is, video 6.8 example 2. So we can run that one as well. Oh, wrong button, sorry. Run that one as well. So the last one I think is NA equals 1. And again you see, apart from rounding errors, essentially PR is 0 if NA equals 1. If you do NA equals 3, that's this one here, then what do you notice? Again, you see this particular structure. If you look at this block here, you see the block is repeated here. If you do PR times LL, what do you notice? 10 to the minus 6 and all these things, essentially you've got 0. What happens if I try NA equals 5? And what do you notice? You look at the PR term and you see you've got a block here, same block here, same block here, same block below. You've got a block here, same block here, and so on. You see you've got this striped structure, which is what you expect from optimal control. And also, you'll notice PR times LL is essentially 0. So that's just reminding you that we've also got video 6.8 example 2. And in both cases, we saw that we got what we expected. What about the impact of feed-forward then? The next few slides give examples that using advanced information with OMPC does indeed improve behaviour, but only up to a point, which is what we discovered when we used GPC. As with GPC, if you use too much advanced information in conjunction with a low NC, it can be counterproductive. Now, we should note that this algorithm is penalizing deviations from steady-state inputs, not input rates, and so this change does have an impact on the responses somewhat. So here's video 6.9, example 1, and you notice the top example, we've got advanced knowledge of 5, and in this example, we've got advanced knowledge of 1. So the original algorithm, no advanced knowledge, this is the sort of behavior that you get. We've got the tracking here, and we've got disturbance rejection over here. So first of all, you'll notice that the disturbance rejection is the same in both cases, and that's not surprising because essentially there's no advanced knowledge there. So the algorithms are equivalent, and that gives you some confidence. However, when you have a set point change, you'll see clearly this one anticipates. You might not like how it anticipates, but let's not dwell on that. It does anticipate, and if you were to calculate the corresponding J's, clearly this top one would give you a slightly lower J than this one below, because it's bridging the errors on either side of the set point change. And also, if you look at the inputs, you'll see that the maximum input here, it stays much closer to the steady state input than this value here. What happens then if I decide to take NA up to a very large value? Here I've taken it up to 15, and what you'll see is this is not good. So if you use too much advanced knowledge in conjunction with a low NC, so here NC was 5, exactly as we saw with GPC, it's not necessarily helpful. You might have an argument about whether the J is bigger or not, and you can probably prove that in fact the lower example does give you a smaller J. But is it what you want? J isn't the be-all and end-all. You might say, I don't want this much anticipation, even if technically performance is slightly better. And we've also got an example 2, which is a multivariable example, and slightly messier. And what you'll see is, again, it's easier if you look at the movement for loop 2. You'll see there's some anticipation there for this set point change here in loop 2, and you'll see the anticipation NA equals 5, whereas down here no anticipation because NA equals 1. And in that particular loop it's fairly transparent. You've got some benefits. Do you think those benefits are worth it? Well, that's for you to judge. If you look at this top output, you'll see it deviates down a certain amount, whereas if you come to the loop below without advanced knowledge, look at that deviation is much, much bigger. And so there you can see it's fairly transparent. You have got some benefits by using advanced knowledge. So this video has shown some code which implements advanced information within an OMPC law. It's clear that the information can be used systematically, and critically it does affect behavior by changing the perturbation parameter C. Up to a limit, using this information is helpful. Generally speaking, I would probably advise against choosing NA greater than NC, although the code I provided, it will do whatever you ask. It will be possible to use trial and error, as in video 6.4, to determine a suitable NA, and that may well be where you end up. But conversely, I think optimal control is slightly different from a finite horizon, and I suggest that if you use something like NA equals NC or close to NC, you'll probably be close to a reasonable result. Now, just a reminder to finish with, this chapter has ignored constraints, and clearly the inclusion of constraints will also have a marked impact on how much future information is useful. But that extra factor, of course, complicates things even more and makes it really transparent that it's quite difficult in general to say what is a good value of NA.